Hello, hello. How is everyone doing? There's only a few of us, but we'll make do. All right. Hey. So let me know how the audio sounds, the video, how it looks. Let's do a quick quality check before we continue forward. I want to make sure nothing happens like last time where the audio got really bad. So ideally it should be good this time. So drop me a comment and let me know if it sounds good. Perfect. All right. So especially if you watched the last stream, I definitely compare it to that. Should sound normal now. So, all right. So, I've prepared a little what I call checkpoint, which is almost like it's kind of like a mini exam almost. So I made one section to this. My intent was to make more than this, but what I'll have to do is later tonight finish the rest of it. But for now, I made one section to this, and it's just covering individual topics per question. And it's a review of all the concepts that we've covered so far, more or less. There's 8 of these smaller problems. So you might find that the problems are either similar difficulty to a test problem or a little bit easier. Nothing should be harder than a test problem on this. It's just to check that you have the right concepts in mind and how to use them correctly. So, is there any questions on anything before we get started? So I assume since you are here that you should know where the download link to this is on my website. Otherwise, go to my website. It's at the top in the announcements section. There's a download to this file right here for the checkpoint. All right. Let's go ahead and get started on this. So let's run through these 8 problems. So in the future, on Monday, and here on out, ideally, these checkpoints will have 2 or 3 sections to them. There'll be an individual topic section with questions like these per topic, but also I'll include a few like multiple choice questions to kind of test you conceptually, make sure you kind of get the idea behind something, and then a few problems that are a little bit more like test worthy, things that kind of combine multiple concepts. So that'll be for Monday, same time, 8 p.m. So the live stream schedule is Monday and Thursday at 8 p.m. And more or less we go for a couple hours. Just depends on what we're doing. So let's go ahead and get started on this. So this first problem here is you go on a hike and you encounter a 250 kilogram boulder on a horizontal surface and wish to move it out of the way by applying a force horizontally. If the coefficient of static and kinetic friction between the boulder and the ground are given, it's 0.75 and 0.40 respectively. So static is 0.75 and the kinetic is 0.40. In general, though, if it's not specified which one's which, the static one is going to be greater than the kinetic one. What is the minimum amount of force that you must apply to begin moving the boulder? So this one, it screams friction in it. It says friction in it, but you should understand how friction works in order to figure out what the minimum amount of force you need to apply is. So here's how we approach this problem. And if at any point, if you have any questions, just toss them into the chat. If for some reason the quality goes down a little bit, like drastically, give me a heads up. Maybe we can troubleshoot it if that ever happens. But feel free to let me know anything in the comments while I work this out and explain how this works. So for problem 1, problem one, we have this boulder that I'm going to sketch out, and we know that there are forces that are going to act on it that I want to also draw in this diagram. So we have the weight of it pulling down. So remember that the weight, or the force of gravity, the gravitational force, will always point down on the object. More specifically, it points towards the center of the Earth if it's a perfect sphere. The normal force does not always point up, but it's always perpendicular to the surface. So given that the object sits on the surface, it's in contact with it, the normal force will point perpendicular to that surface. So in this case, it's up. We have that we're applying a force. Let's assume it is to the right. When we can, we will assume that the motion is to the right when it's vaguely left open. So we're going to apply this force horizontally to the right, call it capital F. And we know that there's this friction force resisting what we're trying to do to it, which is to the left. The tendency of the motion is to the right, so we know that the friction opposes the tendency of the motion. So even if it doesn't move, we know the friction will still try to oppose it in such a way as to prevent it from moving. And if it is moving to the right, then just simply points in the opposite direction to oppose its tendency. Now, so we have this force diagram here, and we want to find the amount of force F, the applied force, that we need to push with to get that boulder to start moving. So we know that from friction, there are two types of friction, static and kinetic friction. So for static friction, so this is a little brief review of the two concepts. In general, we can rate two things for static, is that Fs is equal to, or less than or equal to, the coefficient of static friction, mu s, times the normal force. So remember that the static friction could be any range of values, ranging from 0 to whatever its limit is, which is when it's equal to. So we often write that Fs maximum, the maximum amount of force that the friction is allowed to supply, is when it's equal to the right side. The static friction force cannot supply more force than whatever this value ends up being in the problem. Now, for kinetic friction, it's much simpler. The kinetic friction is just simply that the kinetic friction equals the coefficient times the normal force. And it's the kinetic coefficient. Now, in this case, we're going to consider the case in which we want to just barely begin moving it, but it technically hasn't moved yet. It's the very last moment that before it just starts to move. So it technically is still static. But that last moment before it begins to move is when the static friction can no longer handle the amount of force you're pushing with, and you overcome the static friction, which has to do with the limit, which is the maximum. So all we need to do in this problem is just write Fs max equals the coefficient times the normal force. That's the first step. We know the coefficient in this problem, it's given to be 0.75, but now we need to find the normal force. The normal force can be found by looking at the force diagram and realizing, okay, I have other forces I can compare it to. So I can use Newton's law, sum of forces in the y equals mass times acceleration in the y. We know that this object will never, in this problem, move up or down along the y-axis. Because it's never going to have any motion along the y-axis, we know that it should never accelerate along the y-axis. So it's 0. We set the right side of the equation to 0, and the left side we expand out the forces that have y components. So for instance, we have normal force up, that's positive, and the weight down, mg, it's negative. So there's only two forces that are y components. If there's any diagonal forces, we need to break into components, and then we would consider its x and y components as needed. In this problem, it's very simple because the normal force just equals the weight. Okay. So the normal force equals the weight in this circumstance. We plug it back into the static friction maximum, and we get that Fs max equals the coefficient times normal force, which is the weight of the object in this problem. So since we have everything, we can just plug it in and calculate. So 0.75 times the mass of the boulder is 250 kilograms, and times g, which is 9.8 meters per second squared. So the maximum amount of static friction that you can have, possibly, so let me get my calculator real quick. Let's see here. There we go. 0.75 times 250 times 9.8. Okay. I'm going to put this in scientific notation since the number is in the thousands. So in scientific notation, this is 1.84 times 10 to the third. And we get mass times an acceleration meters per second squared, so it's a newton. It's a force. Okay. So that's it for that one. So this is the answer to the problem, because we establish here that if we were to do a sum of forces in the x direction, we know that the object's not moving yet. So since there's no motion to consider yet, there is no acceleration, which means these two forces along the x are equal to each other. So that could be easily shown by just doing Newton's law in the x, setting the acceleration to 0, writing the force applied minus the static friction maximum that opposes it, and just showing that you just yield the maximum static friction for your applied force. So let me know if you have any questions regarding the relationship between static kinetic friction and any particular problem, and what the conditions are. All right. Any questions on this problem before we move on to the second one? Crystal clear. Question, is static friction always larger than kinetic? The coefficient is larger than the kinetic. So in other words here, when you look at the relationships for static and kinetic friction, what does remain true in these problems is that the coefficient of static friction is greater than the coefficient of kinetic friction. So that relationship does hold. Now, in terms of force amount, it's not exactly clear cut if your static friction or your kinetic friction force in newtons is going to be greater one way or the other. The reason being has to do with the fact that static friction can be any range of values. So I could, for instance, not touch the boulder at all. I can apply 0 newtons of force, and that simply would mean that the friction force is also 0 newtons, because the boulder is never going to move. If the friction force had any value other than 0 when I'm pushing it with 0, then the friction would be responsible for making the boulder move by itself. And in that case, you would get that SpongeBob episode where the boulder just starts moving along the ground to deliver pizza. It doesn't happen like that. So the friction would at best match what force you're applying. So if the boulder will never move, then whatever you're applying better be equal to the static friction, so the forces cancel out and it doesn't move. So in that case, it'd be static friction. Now, it can't keep doing that forever, because as you apply more and more and more force, it has to keep up with you, but there is a limit to how much force you can apply before you reach the maximum static friction, and then at that point, it starts to move. So, to answer the question, since static friction has a whole range of values, let's say the range of values is 0 to 1,000 newtons, for instance. If that was the range, and let's say I found the kinetic friction to be 500 newtons. Okay, so 500 newtons for kinetic friction is smaller than the maximum of static, which is 1,000. But if you had a circumstance where you were applying less force, so you don't use all 1,000 newtons of static friction, you only use like 250, well then in that case your static friction would have been less than what the kinetic would have been. So it kind of just depends more than anything. Hopefully that clears it up a little bit. And you can let me know if that sounds good. Cool, perfect. So let's take a look at number 2. On your hike, you managed to start pushing a 250 kilogram boulder, so this is just a sequel to the last problem. But it took it a little bit too far, and now it slides down a hill which is inclined at 30 degrees. What is the friction force that acts on the boulder as it slides down the hill if the coefficients of static and kinetic friction, respectively, in the same order, are 0.75 and 0.40? Okay. So this problem is a little bit different. We're going to find the friction force, but now on the incline. And in this problem, we know that it is sliding down the hill. So as it slides down the hill, we know that the point of contact between the boulder and the ground is rubbing along the ground, it is sliding. In that case, with the surfaces kind of grinding against each other, it's kinetic friction. So the thing I'm trying to say here is that you don't want to purely base if you use static or kinetic on is it moving or is it not moving. While that works most of the time, it doesn't work all of the time. What you have to ask yourself is if the object slides along the surface. So what I mean by that is if you take into consideration, for instance, let me give you this example. This is not part of the problem, but I want to show you real quick. A circumstance in which you could have the object moving and it's static still, because movement is completely relative. So if you, for instance, had, this truck here, here's a truck, and you have a big, box sitting in the back. Okay, so the box sits on the surface of the truck, and let's say the whole system is moving to the right with some velocity. The thing is that when you watch this system move to the right, you're going to see the box move with the truck. So technically, the box is moving, but it's not kinetic friction that you use, it's static, because the box doesn't actually slide along the surface. So it's really about, is it moving relative to the surface? Does it rub along the surface is what you really need to consider. Now, in this problem, we know for sure that the boulder slides along the surface. So here I'm going to draw the incline. I'll draw a right triangle. Okay, so this represents a portion of the hill it slides along. I'm going to put, a point right here to represent where the boulder is at any time. And I want to find the friction force, which means that I either need to be able to just directly use the equation to calculate that, or I need to consider its relationship to other forces and how they relate to it. So now I'm going to fill this in for the free body diagram, and I'm going to put the weight down like this. So that's mg. It is a tilted surface, which means that the normal force is perpendicular diagonally to the surface. So the object pushes into the surface, and the surface pushes back out perpendicularly. That's the normal force. And because we know that the tendency of the motion is for the object to slide down the incline, in which case it is actively sliding down the incline, the friction kinetic force in this case points along the surface up the incline. So the friction will always point along the surface, whereas the normal force points perpendicular to it. So here's your friction force, friction kinetic. And we also have an angle of the incline. So the angle of the incline, let's call it theta, is put into the bottom corner of the triangle right there. Okay, so first let's attempt to just simply calculate the kinetic friction. If we have everything, we just calculate it. So I will first write that the kinetic friction is just the product of the coefficient of kinetic friction, mu k, and the normal force, n. Now, we have the coefficient. It's 0.40 in this problem. The normal force, now you might be inclined no pun intended, but no shame anyway if I did intend it. The normal force is not always equal to the weight, which you might be inclined to say. In this case, it's not equal to the weight because the normal force is not directly opposite of the weight. That's the first and foremost reason. But you could have other forces along the vertical, and your normal forces are not going to be equal to the weight. So in this problem, what we need to do is draw the axes on the object so we can split stuff into components. So I'm going to draw this axis, which goes right down the middle of the normal force. This is going to be our y-axis, so it's the perpendicular axis. So that's y. The x-axis has to be perpendicular to that which we just put along the surface, like that, and that's x. So positive x goes down the incline, and positive y goes perpendicular up above the incline. Now, to get the normal force, we need to consider Newton's law along the y-axis since it resides along the y-axis. So what we do is we consider everything with the y component, but that also means we need to consider the component of the weight. So what I'm going to do is I'm going to start from the mass, and I'm going to draw from the mass along the y-axis like this, but I'm not going to go all the way. I'm going to stop in such a place so that if I were to draw a line which is parallel to the incline, which is our x-axis in this case, if I draw a line parallel to the incline, that will be the x component. So I need to draw it like this, diagonally. So it's got to go like that. So see how that's parallel, like that. So now, if you do that, if you draw the triangle that ends up facing away from the incline angle, you can show by geometry that the top angle is the angle theta. In that case, now that you have an angle in that triangle, you can split it into components. So on the y component side, the adjacent side, adjacent belongs with cosine, so we say that this is mg cosine theta. And if we need the x component later, it's just good habit or good practice, is mg sine theta, because it's the opposite side to the angle. Now, to get the normal force, we will do the sum of forces in the y direction, because that's the direction of the normal force. So we say sum of forces, y, equals mass times acceleration, y. There is no motion expected along the y-axis ever in the problem, which means that the acceleration has to be 0. So the acceleration crosses out on the right side, and we set the right side to 0. The left side, we take all forces that have a y component and add them up. So in this case, there are a total of 3 forces, but only 2 of them have a y component. Normal force, positive, so write n. And because the component of the weight goes in the negative y direction, kind of digs into the incline, it's negative mg cosine theta, so I subtract that term. Okay, so minus mg cosine theta. That gives us that the normal force equals mg cosine theta. So I can then use that normal force, plug it back in to the friction equation, and I get that it's the coefficient times the normal force, which is mg cosine theta. And at this point, I do have everything. So I can plug this in, and it's 0.40 for the coefficient. The boulder is 250 kilograms. G is 9.8. And we're doing the cosine of 30 degrees in this problem. Inclined at 30 degrees. Okay, so finally, we get the result for this problem is that the friction force equals, so 0.40 times 250 times 9.8 times the cosine of 30 gives us 849 newtons. 849 newtons. And now, yes, the friction technically is in the negative direction. So what we're doing is we're calculating the magnitude of it, because we already accounted for the direction of things. So if we did Newton's law, we can account for the direction in the Newton's law. In here, when you use this equation, you're just going to get the magnitude. So if you want to, if you need to specify direction, it's in the minus x direction, or up the incline. Let me know if you have any questions on problem 2, and we'll go from there. You can also give me just a thumbs up if you just want to slap a quick, okay, I got it, just to kind of give feedback. So thumbs up are pretty good to signal that I should just keep going. No questions on this one? Everything looks good? I'm going to switch this over. All right. So problem number 3, you have a 30 centimeter long spring which is attached to the ceiling, initially with nothing connected to the loose hanging end. A 2.5 kilogram mass is then connected to its end and allowed to come to a new equilibrium point, which is 10 centimeters below where it was initially. What is the spring constant of this spring? All right. Ah, you found the thumbs up. Cool. Emoticons are one of the greatest inventions of the new millennium. Go the human race. So, for the third problem, looks like we're good. Okay. So, problem number 3. We're going to draw our little spring, and the spring is stretched out because we've loaded a mass onto it, and it just pulls it down a little further. So here's the ceiling, here is the spring, and then down to a connected mass. So let's just say that, you know, the spring is initially this long from here to here. Let's call this length L. And that's the natural preferred length of the spring, which is in this problem given to be 30 centimeters. So it's equal to 30 centimeters. And we know that we are stretching it an additional distance, and we represent that stretch by the variable x. So here's our additional stretch, x, down to where the mass is. And x, in this problem, I tell you that it is 10 centimeters below where it was initially. So the exact value of x is literally just 10 centimeters. In some problems, what I'll do, or what in general we'll do, is give you the new length of the spring, and you'll have to subtract the new length from the natural length of the spring to get how much of it is stretched. So in this case, we just have the distance of it stretched or compressed. The way I do this is I actually disregard the positive or negative nature of x, representing compression or elongation of the spring. So I just used the absolute value, in this case 10. Now, when I'm going forward with the problem, we may talk about spring forces or work done by spring. Those are a couple of things we'll talk about through the class. So in any case, I will always ignore all signs on those equations until I want to determine the sign at the end, is the way I handle it. So if we need to, for instance, calculate the spring force, I will just say it's k times x, and I'll deal with the direction later. Now, let's start with what we want. Now, in this case, I want the spring constant of the spring. So the equations I mentioned, which is the work done by the spring and the spring force, are a couple of equations that should come to mind when you think about spring constant. Now, if we could just talk about forces, okay, so if we could just talk about forces, which in this diagram, it's the weight downwards, and because the spring is stretched beyond where it wants to be, the spring force will always point towards where its natural length is. So if the spring prefers to be at L equals 30, then it's going to point upwards to try and pull it back. So we're going to label that as the spring force capital F sub S. Now we also know that this is an equilibrium in this case. I tell you that it reaches a new equilibrium. So I know that these two forces are just equal and opposite in my case. So now we do sum of forces in the y equals mass times acceleration in the y. So there is no acceleration in the y because it's in equilibrium. It's equal to 0. Sum of forces in the y, we have the spring force upwards in the positive y and the weight downwards. So that's the spring force minus mg. We can actually say that the spring force is then equal to the weight. And we also actually know what the spring force is equal to. The spring force is also equal to k times x. So I can take this spring force, I could use it to solve for the spring constant, but I could actually also just substitute it into this equation. So I can write that k times x, the spring force, move the mg over to the other side, is just equal to the weight. With this, I can plug in and solve for this. So it's just the weight over the distance of stretch or compression. And we have that it's the mass that's hanging. In this case, it's 2.5 kilograms. G is 9.8 meters per second squared, divided by x, which is 10 centimeters, so it's 0.10 meters to be consistent in units. And k is 2.5 times 9.8 over 0.10. So we get 245 newtons per meter, because the top will give us newtons and the bottom has meters. So that's the units of the spring constant. Now, so you can think of a couple of different routes that you can use to get the spring constant, but you always want to try the easiest route first. So in this case, the easiest route was to consider the spring force, given that you know the distance that stretches, and that you can use this, you can use Newton's law to find the value of the spring force so that you can solve for k. So let me know if you have any questions on spring forces in general, or give me a thumbs up. All right, looks like we're pretty good. So I'll switch that back over. All right. So let's see here. Problem number 3, springs. Problem number 4 is on circular motion. I tried to also put this in a topic order for this. So if you kind of are organizing things in your head as far as the topics you learn, these are actually roughly in order of the topics too. So problem number 4, we have a ball with a mass of 500 grams. It's attached to one end of a 0.5 meter long string while you hold the other end of the string. Assume that you twirl the string around in a circle vertically. Orientation does matter often, in such a way that the speed of the ball remains constant at 15 meters per second. What is the tension in the string when the ball passes through the top of the circle, when it's oriented vertically as far as the circle is concerned? So now, for this setup, you should already recognize, okay, so I have a circular motion problem. What do we do with circular motion problems? So a lot of times, you will end up using Newton's law if you have to involve the forces in the problem, which in this case I'm involving the tension force, so I need to talk about Newton's law. So we'll write out our diagram. So here is the circle here with the mass at the top of this vertical circular path. Here is the center. Here's the string that connects it to the top. So what I'm doing is I'm twirling it around and it just goes through this circle here. So we draw the forces because we want to find the tension. So the tension will always point away from the object and directly along the string, so which means it goes straight down like this. We also have that it has mass, so there's gravity pulling on it, so then we have a weight, also downwards. That one's always down. Okay, so this is the free body diagram for this object that's traveling in a circle. Now, we are going to apply Newton's second law, sum of forces, in the... Now, when you pick a direction in this, you have to realize that because you're doing it in a circle, you have to consider what we'll refer to as the radial direction, or the r direction. So sum of forces in the r equals mass times acceleration along the r. R is just the radial line, or the radius. So anything that points toward the center, now you could choose the signs however you like, but from my experience it's better to put positive towards the center, so I'm going to do that. I'm going to say that anything, any vector that points toward the center is taken to be positive. And if it's not pointing towards the center, if it points away from the center, it's negative. So that's going to be my coordinate system. So this is tricky because normally when we think upright, we say up is positive and down is negative. Well, in circles, it's not going to matter as much if it's up or down. It's going to matter, is it toward the center or is it away from the center? So in this case, I have my two forces at the top of this. They're both pointing down, but that's toward the center, which means that they're both taken to be positive rather than negative. So this isn't so much of an issue in this problem, but in other problems, especially when you have other forces that point in the opposite direction, you can screw up the signs and end up getting it wrong for not being consistent with that. So the right side, now I don't know anything about the acceleration, but I do know that in circular motion there has to be a radial, or in other words centripetal acceleration. So this value for this acceleration cannot be 0. But we do know that it expands out as v squared over r. So it's mass times v squared over the radius of that circle. On the left side, we write all the forces, which we said are both toward the center, so they're both positive. So T, positive, plus mg. We want the tension in this problem, so we move the weight over to the other side, and we get the tension. Tension equals mv squared over r minus the weight. To make our calculation just a smidgen easier, I'll pull out the mass, factor that out. So we have equals mass, then quantity times v squared over r minus g, that whole quantity there. And let's substitute the numbers and let's calculate this. So the mass is going to be, in this problem, it's a 500 gram mass, which we need to put as half a kilogram. So 0.5 kilograms. We have the speed is going to be 15 meters per second. So 15 meters per second, square it, divided by the radius, which is, now I don't tell you the radius in this problem, I don't say explicitly radius, but I do technically give you the radius. It's disguised as the length of a string. So you'll notice in this case here, so let's go over to here, you'll notice in this diagram where I tell you, hey, here's the length of the string from, you know, where you hold it to this mass here. If that's the length of the string, well, if you're twirling in a circle, that is the radius of the circle. So it's just kind of cleverly hidden in the information. So that's the radius of our circle. So we use 0.5 meters, and then we subtract off 9.8, meters per second squared. And let's calculate that. So 15 squared is 225. So 225 over 0.5 is 450. 450 minus 9.8. Minus 9.8. 9.8 times 0.5. So we get that the tension in this rope or string is 220 newtons. So this is how you're going to use circular motion to solve a problem like this. Sometimes, we'll ask, for instance, what the acceleration is, in which, you could either use v squared over r, or you can relate it to the forces again. But a lot of problems will involve relating the forces to what it's doing, which usually implies writing Newton's law and recognizing that the acceleration needs to be v squared over r. Now, if I were to hypothetically ask what happens through the course of this problem, let's say as the ball goes to the bottom of the circle, what you will find is that when it gets to the bottom of the circle, the forces will point in different directions. For instance, the tension would be upward, the weight would be downward, and you'll get a different answer for the tension. In that circumstance, you would get that the tension is bigger at the bottom and smaller at the top. So, because at the top, the weight is actually trying to pull it down, so it kind of alleviates the stress on the string and brings the value of the tension down, whereas at the bottom of the circle, the weight actually pulls down and tugs on the string and makes it have more tension. So, conceptually speaking, that would be it. So let's go to number 5. Number 5, you have a 20 kilogram object which sits on a flat horizontal floor. You apply a 500 Newton force in the direction that is 10 degrees above the horizontal, while a friction force of 250 newtons resists the motion. What is the work done by the friction force over a 10-meter distance? So there's actually a couple pieces of irrelevant information in this problem here that was intentional. So the thing is, I want the work done by the friction force, and I could just use the definition of work with the friction to just calculate that, as long as I can calculate what my normal force is. So we might not really care so much about a couple of little details in this problem. So you might say, okay, if I were to calculate the work in this problem, my work involves an angle. You might have a habit of dropping in that 10-degree angle into there, but that's only used if you're going to calculate the work done by the applied force here. So let's see what happens with this. I can write in this problem, once I write my diagram. So I have for problem 5, here's your surface with the object, and all of our forces are going to consist of the weight down, normal force up, perpendicular to the surface. The force applied is at an angle above the horizontal. Let's call that angle theta. Theta is 10 degrees in our problem. And we have a friction force which resists the motion because we're going to move it 10 meters in the direction to the right in this case, since we're pulling it to the right in our diagram. And the friction, we know it's kinetic friction, would point to the left. Now, to calculate the work done by the friction, I could simply write that the work definition is force parallel times distance. So specifically, you can calculate the work as long as you use the parallel component of that force to the direction you're displacing it. So in other words, if my motion in this picture is to the right, then I just want the parallel component of whatever force is in question. So if it was the applied force F, I would break it into components, and I would find it's the cosine component, which is the one that goes along the direction of motion. I would also find that because the normal force and the weight are perpendicular to the motion, that there's no work done by those, because there's no parallel component to the motion. The friction is anti-parallel, in other words, oppositely parallel to the motion, which means that you would get actually negative work. Now, if you want to, you can also just directly expand this out as force times distance times cosine of some angle, I'll call it phi. And the thing is if you use cosine in here, you have to operate on one definition for that angle. And the definition is that it must be the angle between the direction of motion and the force in question. Whatever force you were asking for the work done by, it has to be the angle between whichever way it's being moved and the direction that the force is applied in that you're questioning. That could be any of the forces. So now, in my case, I want to know what the work done by the friction force is. So the work done by friction is going to be, that's right, work friction equals the friction force, Fk, times the distance that I move it, call it d, and the cosine of some angle, which we look at the picture and we say, well, the motion is to the right, but the friction force is to the left, so if they're opposite each other, the angle that spans between them is 180, not 0. So we use 180 for that. And cosine of 180, if you don't remember it, you can calculate it pretty easily. It's -1. So that's where you get the negative work done from. So it's negative. The friction force, now in this problem, I actually give you the friction force, the exact amount of friction force, and I gave you it as 250 newtons. Normally, in a lot of problems, you won't be given the friction force in value, but rather what you'll be given is the coefficient of friction, and it is left up to you to go find the normal force. So I'll give you a little reminder here that you could say that the friction force equals the coefficient times the normal force, but we don't need it. So this is what makes a couple of pieces of information irrelevant in this problem is, for instance, I tell you you apply 500 newtons of force. I tell you you apply it 10 degrees above the horizontal. And I also tell you, oh, the mass is 20 kilograms. Those pieces of information in this circumstance are not needed at all, simply because we don't need to talk about the normal force, since I already give you friction value. So in other problems, the route you would take is finding the normal force, set up the forces in the y. You would find it's not equal to the weight in this problem. The most common mistake in this problem, or one of them, is to say it's equal to the weight when it's not. There's other forces other than normal force and the weight. So in this case, it's a component of the applied force. But that's where you would use that information. You would only use that information from the applied force to then find the normal force, to then find your friction. But you have it. So, in this case, I'm just going to drop it in. The friction force is 250 newtons in magnitude, times the distance you displace it, which in this problem is given as 10 meters. So 10 meters. So very simply, the work done by friction is negative 2,500 joules. That's it. So a lot of that work is avoided simply because I gave you the friction force instead of its coefficient and making you find the normal force. So make sure you know how to do that if you're being asked in that circumstance. But this is the easier version of it. Any questions so far? This one was hopefully relatively easy. Okay, let's carry on. So, number 6. Lightning is ultimately a ton of electrical energy released in a very short time. If the power of a lightning bolt is 10 to the 9th watts, and it releases the energy over a span of 50 times 10 to the... you'll need to correct that actually. It's 10 to the -6th. Lightning does not take that much time to happen. 10 to the 6 is a million seconds. So change that to a minus sixth. It's also written as 50 microseconds. So that's the time interval. What is the amount of energy it released? So this one you should just realize, okay, I want to talk about energy, power, the time it spans over. So it's just the definition of power. So power, by definition, is P. It's defined as or equal to the amount of work done divided by the time interval. Now the work done is just a transfer of energy. Work is energy going from one place to another. So it really is just energy you could replace it as. So if you know the energy that's involved, then you can use it in that place, since work is just a transfer of energy. So we need to solve for that energy amount. So we're solving for the work, which is power times time. The power is 10 to the 9th watts, but a watt is a joule per second, because a watt is a unit of power, and you can look at the units of this and it gives you joules per second. So joules per second, just to show that it cancels with the seconds, which is 50 times 10 to the, and the correction is 10 to the minus sixth seconds. So we calculate this out. This is pretty easy because you just have powers of 10. So you have 10 to the 9th, 10 to the minus 6th. You put them together, it gives you 10 to the 3rd, and you just carry the 50 through. So it's 50 times 10 to the 3rd joules. You can either express that as is, you can just leave it there. It's not a big deal. It's not in proper scientific notation, but it's kind of nice because it actually tells me it's 50 kilojoules because of the 10 to the 3rd. Or if you really want to put in scientific notation, it's just 5 times 10 to the 4th joules. Okay? So that's the amount of energy that's released in that problem. So that one's just pretty straightforward. Just make sure you know the definition of power and just apply it. So now we go on to the last page. Let's see here. Let's go to there. So the last page. Problem 7 and problem 8. A 5 kilogram mass sits on a horizontal surface and is attached to a 25 centimeter long spring that is connected to the wall at the other end. So on one end you have the attached mass, and on the other end it's attached to an immovable wall. If the spring is stretched 10 centimeters from its natural length, which I gave you to be 25 centimeters, what is the work done by this spring on the attached object? So this, we can just use the work done by a spring, which has a special formulation because the force is not constant as you stretch it. In many other problems, we talk about a force being applied over some distance, but that force often remains constant, it doesn't change. In springs, let's say that, our equilibrium point of the spring, its natural length is somewhere over here, and we stretch it out this distance. Well, when the mass is at the natural length of the spring, so then the spring is its natural length, it's not stretched or compressed, so there's no spring force. But as you pull it a little bit, stretch it a little bit, suddenly you have a spring force. You pull a little bit more spring force. Pull it more spring force, etc., etc., etc. Because the spring force grows with distance that you stretch it or compress it, you don't have a constant force. You would otherwise need to use calculus on this problem, but luckily it's already taken care of. We just give you the equation for the work done by the spring. So here's how we use it. The work done by a spring is problem 7. So you have a spring that is, in this case it's stretched, but in general, the work done by the spring, Ws, the magnitude of it anyway, is 1/2 K, which is the spring constant, times quantity x final squared minus x initial squared. The reason why I'm starting in general with this is because I do want to account for cases where you don't start from 0. Because in the special cases, which happens a lot actually, if you start the spring from equilibrium, the equilibrium of the spring anyway, its natural length, the x value, this how much you're stretching it or compressing it, when it's at its natural length is 0, in which case it just becomes 1/2 kx squared. But in general, if you take it from a place that's already stretched and you bring it to another place where it's even more stretched, then you need to consider this here. It's not just 1/2 kx squared. So, in this circumstance, we start from x initial being 0 because it was not stretched nor compressed initially. Okay. So we can boil this equation down to what it often becomes, which is just that the work done by the spring is 1/2 spring constant K times x final squared, where x final is just how much you stretch it from equilibrium, the equilibrium length. Now, again, we're only going to get the magnitude of this by doing this. So this will only give you the magnitude in general. That's easy though. You can take care of the sign plus or minus by just analyzing it conceptually. So for instance, realize that you are starting here. This is x initial equal to 0. And you are ending over here, where x final, how much you stretched it, ended up being 10 centimeters from its natural length. So it's 10 centimeters, which is 0.10 meters. Given that you know that you move from here to there, which means you're displacing it to the right, so I'll say that we're displacing it some distance x to the right, and also knowing conceptually that the spring doesn't want to be that long, meaning that the force provided by the spring points back towards where it prefers to be, to the left, those two are in the opposite direction. The work is a measure of the ability to influence the motion of the object. And it is positive when it is helping it to move the direction it's moving in, or it's negative when it's in the opposite direction of what it's trying to do. So since you're moving this mass to the right in the opposite direction that the spring force points, it works against it, which means it's a minus sign. So we're going to write that the work done by the spring with the correct sign on it is actually negative in this case. 1/2 kx final squared, since Fs is opposite to motion. Okay. So this will give us the correct sign for the work. Now we calculate this. Now, do we have the spring constant in this case? We do not have the spring constant. Did I give that to you? 1 second here. You know how long the spring is, you know how much it's stretched, and then what is the work done? Okay, so I either needed to give you the amount of force that you're pulling with on it, which I actually didn't in this case. Whoops, space that out. Or I need to give you the spring constant. In this case, I'm going to just give you the spring constant. So I'm going to add in that the spring constant is 100 newtons per meter. So let's use that value for that. Add in K is 100 newtons per meter. Okay. So that's minus 1/2 spring constant, let's say it's given, newtons per meter, times the distance that we stretch it, which is 10 centimeters, but it's 0.10, for meters. And then don't forget to square it. So we get that the work done by the spring is negative. Actually, 0.10 is 1/10. So if you square a tenth, you get 1/100th. It cancels out the 100 there, and you actually just get minus 0.5. So it should be minus 0.5 joules of work. Now, I do want to consider the hypothetical scenario, which is also pretty likely as a question, which is if I don't give you the spring constant in the system, you would need to know how much you're stretching it or compressing it and the force that's needed to get to that point. So, for example, here's a separate hypothetical, is let's say if you knew that you were applying a force of let's say 1,000, is it 1,000? No, if I do 0.1, let's use 10. I think it's 10 newtons. Let's say 10 newtons. And that's the force that you need to basically stretch it that far. And you know that you're stretching it, 0.10 meters. You could actually take this information and relate them by using the spring force, since you are saying this is basically the spring force. You could then use the spring force equation. So again, magnitude only, ignoring direction. Solve for that spring constant. Plug in the numbers, 10 newtons divided by 10 centimeters, which is 0.10 meters. And you would find the spring constant to be 100 newtons per meter. So that would be the hypothetical scenario where you don't have the spring constant, but you do have something else that's closely related to it. So it's either I wouldn't need to give you the force, or I just hand you the spring constant, one way or the other. So let me know if you have any questions on springs, and we'll take a look at the last problem. So now the last problem will encompass the last topic that was covered. So this is in chapter 7. It's on the work energy theorem. So you have a fun roller coaster ride. It has thrill seekers in a cart with a total mass of 2,500 kilograms. The cart is brought up a hill and reaches the top, where its movement is negligible, meaning that we're going to assume it is at rest. Realistically, if you're talking about a roller coaster, it moves very, very slowly at the top. We're going to say it's 0 on this problem. The cart then drops down the other side of the hill so that the total work done on the cart is given 9.2 times 10 to the 5th joules until it reaches the lowest point, that is 39 meters below the top of the hill. So in this little diagram here that I drew out, just for a little cool thing to look at, you have the top of the hill here, and the hill that you go down descends 39 meters until you get down to this point here. Okay, so if you need that piece of information, it's 39 meters downwards till it gets to that bottom point. We're going to calculate the speed of the cart at its lowest point. So we understand that there is work being done on the system, and we know the exact amount of the total work done. There are maybe multiple forces doing work on this system, but we're not going to really care so much about the work done by any individual force, whether if that be the weight, the work done by the null force, if there's friction. We're not going to worry about that so much, because the problem first never asked you to care about it. Now, but then you might say, well, what if I need to care about it later? Well, look at this. If I just want to know what the speed of the cart is at the lowest point, and I know I'm going to go from the top where it starts at rest to the bottom where it's not at rest, and I know the work done during that process, they're going to be closely related together. And the thing is that if you know the total work done on the system, or the net work, you can just relate it directly to its change in kinetic energy without any questions asked. So what I mean is, specifically here, problem 8, Looks like we're good on questions. Okay. So, okay. So, problem 8. We have the total work done, or the net work. So what we have is sum of all work, sigma W, just like sum of forces, equals the change in kinetic energy of the object. And that's K for kinetic energy, not spring constant K. This is also known as the work energy theorem. Work energy theorem. This is also known as, here's another name that we'll learn about actually, in the next couple of days, is it's also referred to as the conservation of energy theorem. Okay, we'll refer to that later, but for now we're going to call it the work energy theorem. Now, in the work energy theorem, it states that if I know the total amount of work done on a system, that could be through multiple forces, each doing work and then adding up to a total, it will tell us what the change in kinetic energy is, which is really just a way of saying, well, is it going to change its speed or not? And I can solve for that speed. So I can write that I do know the net work. So I'm going to leave that alone and plug it in at the end because I know its exact value. So sum of all work equals, the change in anything is always the final minus the initial. So that means it's K final minus K initial. So provided that I never knew the information about the change in kinetic energy directly, I expanded out. The definition of kinetic energy is that K is defined to be 1/2 mv squared. So I write in here 1/2 mv final squared and 1/2 mv initial squared. So all work, or the net work, is 1/2 mv final squared minus 1/2 mv initial squared. Now, because kinetic energy is literally the energy of movement, if you're not moving, you don't have kinetic energy. So at the top of the hill in the problem, so real quick sketch, here's the hill, goes down like that. Okay? At the top of the hill, the speed is 0, or taken to be 0 because it's negligible in the problem. At the bottom, we're going to solve for what that speed is. Okay? Now we were given the height, but do you realize so far that if I don't have to do anything with the net work, because I know its value, and all I'm doing is solving for velocity here, I don't need to know the height of the hill. It's already kind of, in a sense, built into the total work done, because the height only comes into play when you want to talk about gravity pulling it down through some height, which we'll go more into later on another day. Now, let's take this, we simplify it, because we realize there is no movement initially, so we can just get rid of the initial term. No speed initially. So all we have left is the net work equals 1/2 mv final squared. We solve it for v final, so we're going to multiply by 2, divide by the mass, and finally square root it to get the final speed. So v final is the square root of 2 times the net work done divided by the mass. So we solve this, get that, and we have everything. Plug it in. 2 times the net work is given in the problem to be 9.2 times 10 to the 5th joules of energy, divided by mass, given in the problem to be 2,500 kilograms. Okay. So the final speed that the cart reaches after falling down the hill is going to be 2 times 9.2, 10 to the 5th, divided by 2,500, square root, and that gives us 27.1 meters per second. 7.1 meters per second. So this problem has a sort of kinematics-like feel to it, where you have kinematics quantities like its initial velocity, its final velocity, You know, the distance it falls through, it kind of has a kinematics-like feel to it. The only issue is it's kind of a little more complicated to use kinematics on a curve. So we don't really care about the details. We just say what's the energy up here, what's the energy down there. And we find how much work is done, and we just solve it like that. So we only need to care about the energy involvement in the system. We don't need to care so much about the direction of anything. Exactly. So let me know if you have any last questions on either this problem or anything related, and we'll wrap it up for the night. In the future, I will add a couple more sections to this, so we'll have a couple more conceptual questions and a couple more comprehensive examples that combine concepts together to make you kind of really solidify your understanding of the topic. So, any other questions before we call it a night here? I have a couple little small announcements which are based off of my website and future live streams. So, looks like we've got a question. So, so again, the schedule is going to be that every Monday, every Thursday at this time, 8 p.m., we're going to do a live stream like this. We're going to cover everything up to, since the last live stream. So this time, it's everything since the last exam. Next time on Monday, it's going to be everything going back to what we did today. It'll give you a chance to refresh the material again. Now, live stream related, next week is, I believe it's the week before the exam, so I'm going to have some additional live streams, and that information is going to be announced on my website, so you can just check it from time to time, and you'll get the announcements on my website. I'll post the link in this description or the chat if you want it, if you forgot it for some reason. We'll go over more practice exams at the end of next week eventually, and I'll announce those when it gets to that time. Other than that, recheck my website every so often. I have a regular schedule that I have where I'm going to be posting worksheets pretty much almost every weekday, Monday through Friday, morning and evening. I have a schedule I'm going to start committing to where I'm going to upload new content, so new worksheets, more solutions, so you can have practice problems to do basically on a regular basis that will keep you up to speed in class. So with that, thanks for tuning in, and I'll see you next time. One last question. The last question is for number 7. Is the 25 centimeters not necessary? The 25 centimeters is not necessary, new, because I already told you how much it was stretched, which is 10 centimeters. So that's about it. All right. And I think that's about it. So if you have any other questions, shoot me an email, and I'll answer any other questions that you have. All right. Have a good night. No problem.